Alright, let's review piecewise defined functions. Here you have two or more functions that describe an overall function, but usually each piece has a certain constraint to it. So to start, we'll look at two equations for a line. The first one let's simply call 2x plus 1, and then we'll consider another equation that will be negative x, we'll say minus 1. So I can draw a quick graph for each of these. For my first one, I have a y-intercept of plus 1. I'm going to rise 2 and run 1 for the slope, so that would put my point right about here. If I draw a line, say that my equation looks something like this. For the second one, let me switch pens. Our intercept is at negative 1, and our slope is negative 1. So go down 1 over 1. So you can see that this line has a negative slope. It might look something like this. Given these two values, you can see that you can graph those both on a coordinate plane. Now let's add some constraints. Let's say here we only use this equation if x is less than or equal to 0, and we only use this one if x is greater than 0. So this is my x-axis, this is my y-axis. So for these constraints, I'm concerned with what's going on the x side. So this top equation, 2x plus 1, is the one that's in blue. I'm only going to use that equation if x is less than or equal to 0. So that would be all values of x from here, the origin, over to the left. So I can essentially erase this part of the line. For x is greater than 0, I'm going to use the red line. So any point from here over, I'm going to be concerned with. But notice that doesn't include x. So if I switch to black, what you'll see, below x, I'm going to use this equation. And I'm going to put a closed-in circle here. When x is greater than 0, I use my other equation, so open circle, any value out to here. What is drawn in black right now would be the correct answer if you were asked to graph piecewise defined function 2x plus 1 if x is less than or equal to 0, negative x minus 1 if x is greater than 0. So even though we drew the rest of this red line here and the rest of this blue line here, we ordinarily would not include those. Those were just shown as intermediate steps. Black would be the final and appropriate answer. A couple other things that we can do for this. We can talk about the domain and range for each piece. So for the blue line, domain would be any value, including and starting 0 for x. Since this line extends this direction infinitely, we can have x values that get larger and larger. Infinity. Range for the blue line. Right here you can see my y values stop. Go up to infinity. But as I come back down, I have to stop at including 1. My lowest number is 1, and I can go up through positive infinity. If I consider the red line, second equation, my domain for this, any x value out to the left, then I have to stop once it gets to 0. So negative infinity to 0, but not including zeros. My range is going be my lowest value, -1, but it's an open circle, so parenthesis, and my y values can keep going higher and higher, and they never stop. So those are the domain and range for each of the functions. If I want to consider the entire function, so what's defined in black, we can do that in a black pen. My domain is all negative values of x. Once I hit 0, I include 0, and then I jump down here, and I continue to go out for all positive values of x. So negative x, negative infinity to infinity. The range is any value down here, so negative infinity, and I can come up to +1. If you look at our black graph, there are no points in the y-axis above 1. So that's our domain and range for the entire function. So the way you would typically see this written completely would be f of x with a bracket to include both of these. So this would be the domain and range for f of x. This right here is the domain and range for a single component. And this is the domain and range for that single component. There's lots of examples of these in your book. So I would suggest trying those and making sure that you understand these concepts. The other thing that we covered in that final class was graphing inequalities. So if I have the equation 2x plus 1 I'm going to sketch how the graph would look different for each of these. For this top one, I'll call the graph right here. I'll call this one down here. And finally, this one's down here. Plus 1, we'll get a line that looks something like this. I'll have the same line for each of these. Notice that these are greater than or equal to. That's why there's a solid line, because those are included. If you have greater than or equal to, we use closed brackets, and we'll use a solid line here. If you have greater than or less than, we would typically use parentheses. We'll indicate that with a dashed line. So for this one, because those answers are not included, they're a barrier, I'm going to use a dashed line. So if you remember when we made number lines, we had to consider what was going on to the left or right of the number that we're interested in. So the same thing is true for this, we just have to consider two dimensions. So if y is greater than or equal to 2x, you're looking for values of y that are greater than the line. And so we would shade the region above. If you're looking for values of y that are less than the line, here you would shade underneath. And so where we're shading means that any answer chosen from this part of the graph will satisfy the equation. Since this is less than, same thing, we shade up to, but not including the line. One way you can check to make sure is to plug in a point and see if it's in the shaded region. I usually pick the origin because math with zeros is often easier. So for this equation right here, if I put zeros in, I get 0 is greater than or equal to 2 times 0 plus 1. If I simplify that, I get 0 is greater than or equal than 1. That's false, so that point should not be shaded. And you can see if we look here, it's not shaded. If I plug 0 in down here, I get 0 is less than or equal to 2x plus 1. Substitute x for 0, and I get 0 is less than 1. That's true. So that should be shaded on my graph, and you can see it is. And then the same thing would be true down here.